Enric Florit, who is the student of the University of Barcelona. He's studying mathematics and informatics at WWE, and he's also working in AutoCAD in cryptography. And well, that's what he's actually going to talk about, the postquantum cryptography.
Okay, so thanks, Adriana. Well, we will talk about postquantum cryptography, what, why, and how. Actually, the title is a bit swapped here because it should be why, what, and how, what we're going to do. And so, let's begin with reviewing Diffie-Hellman. Let's say we have two peers, which we'll call Alice and Bob, who want to communicate over a large distance, maybe over some channel. Someone could be listening. And, well, if they have the ability to meet, they could just meet one afternoon, start crossing coins, generate some key to exchange their messages. But what if they are very far apart, they have never met? How can they exchange some key to encrypt their communications? Right? So in 1976, Diffie and Hellman proposed a simple way of doing this. We just have to take a cyclic group, let's say Z modulo P, the unit of Z modulo P, which is all the integers between 1 and P minus 1. And we choose a generator alpha, and then Alice will pick some random integer between 1 and P, which we'll call A, and will be her private key, lowercase a. And then, raising the alpha to the lowercase a, we can get uppercase A modulo P, and she will send that to Bob. Then Bob will do the same. He will generate some random integer between 1 and P, and compute his public key and send it to Alice. Then each other can raise the public key of the other part to their own private key. And they will get because this AB commute, they will get the same alpha to the AB, and they can use this as a shared secret. And so what's the security of this? We have to look at two computational problems. The first one is the discrete logarithm problem, which is if you have a generator alpha and you have a public key beta, get the x. Okay, this will work the same as logarithms in calculus, but it's discrete because the set we are working with is a finite group. And then there's the Diffie-Hellman problem, which basically says you have two public keys. You actually don't know a bit here. Okay, you just know what elements are. Get the shared secret directly. Obviously, we have a solver for the discrete logarithm. It's trivial to solve for the Diffie-Hellman problem, because we can recover the private key of some part and then act as this part to get the shared. Right? Now, let's try to solve the discrete logarithm problem. Yeah, so let's keep in mind this, alright? The first thing we can try is doing an exhaustive search. Let's say, right, that n is the order of alpha, so that alpha to the n is equal to 1 in the group, right? And we want to solve, to keep this in mind, beta equals alpha to the x. The first thing we could do is raise alpha to every possible integer from 1 to n and check when it's beta. This is horribly slow because the size of this group is represented in log n bits. Alright, so everyone here knows O notation. Right? So this will take O of n, so in n group operations, so alpha to the n, we will get eventually beta. But this is exponential in log n, so this is a very bad complexity. The next thing we could do is an algorithm which is called baby step, giant step, which is based in this. Let n be about greater than but about the square root of n. Then if we take an integer which is smaller than n, we can divide it by n, and then the quotient and remainder will be between 0 and n. Right? So with this, we can pre-compute alpha to the b for every b between 0 and m and store them, right, in a hash table. Then we will compute all these values, but not storing them, but looking for this in the previous hash table. And then for some integer, for some A, this will coincide with some element here, and then we will be able to solve for beta, and then x will be this number. So this has complexity square root of n in memory, which is kind of bad, but, and square root of n in time, because we are doing 2 loops of this size. Then, so this complexity here is optimal if we only use the operation of the group. But if we use the structure or the order, we can get better. One strategy, if we use the order of the group, let's say we have n factored as a product of powers of primes, then we can obtain x, the discrete logarithm, modulo each of the powers of primes, and then combine them using the Chinese remainder theorem. How are you going to do it? Well, if you raise this equation to n divided by the power of the prime, then you're working modulo b to the factor. So if you can compute it here, using maybe the previous algorithm or some other ones that require less memory, and then you're getting x modulo b to the. There's a problem, of course, if n has prime factors that are very big, this will not really work, and we have to factor it moreover, but we can get partial information. Okay? And then if we use the structure of the group, for example, if we take discrete logarithms over finite fields, what are we going to do? Well, we pick a factor base, this is a set, and using all the elements of this set, we are able to generate most of all, or ideally all, of the elements in the field. All right? By the way, I'm working in the multiplicative group of the field, so I'm removing 0. So for all elements of this factor base, we have to know the discrete logarithm. And then if we have some relation of this kind, which is easier to find because we have this alpha to the k, and we can play with the k, and with this factorization, because logarithms have this multiplicative additive property, we can just solve for x, right? Because we just take the logarithm of this product and we subtract k, and we will get the logarithm. Right, so what's the complexity of this? Look at this nice formula. So we have seen that there are polynomial and there are exponential complexities, but everything in between is expressed basically with this formula. Because if t is 0, then we'll get a polynomial complexity in log n, which is what we are doing. Well, n should be uppercase with. And if t is 1, then this will be exponential in log n. Right? So everything in between, sub-exponential, or super polynomial if you want. So we have said the exhaustive search has O of n complexity, then baby step, giant step has O square root of n for both time and memory, but we can get with memory of 1 for some other algorithms. Poly-Hellman is some strange thing that basically depends on the biggest factor. Then we have the index calculus, which is halfway. The square root of 2 is not really important for right now. The important part is the half. So it is halfway between polynomial and exponential. And then we have the number field sieve for solving discrete logarithms. This is the best algorithm we know. It's also the best algorithm we know for factoring integers. And it's also super-exponential, but it's better because it's 1/3, not 1/2. But even sub-exponential is a variable complexity, and if we make our groups large enough, we should be secure, all right? But this is only for classical algorithms, and we are talking here Postquantum. So in 1994, Peter Shor published an algorithm for solving integer factorization and discrete logarithms. So in polynomial time using a quantum computer. I'm not going to explain it because I don't really understand it, but the thing is we should be secure, right? Because quantum computers are not really a thing, right? Right? So the thing is there are already some reports by the PQ Crypto in Europe and saying that everyone is investing huge amounts of money developing these kinds of machines. Also the NIST, the National Standards in the United States, has said a couple of years ago that, well, maybe in 20 years or so we have large enough computers so that we have to worry. But the thing is we already need to change the encryption we use. So that's why we need cryptography because it looks like the developments will be will be relatively small. So, what is postquantum cryptography then? Well, we need two requirements. The first is postquantum cryptography has to be usable with current hardware. Our computers, our phones, low power devices, everything has to be able to use the new algorithms. It cannot be something too complex for us. And then, but we have to be resistant to both classical and quantum cryptanalysis, right? So there's this new requirement here. If there's a polynomial algorithm in quantum time, in quantum computers, it's not feasible for us, it's not usable. The thing is, we only need to develop public key cryptography because, well, of course, public key cryptography is based in discrete logarithms, integer factorization, these kind of problems. And so we need to look for new kinds of encryption. However, for symmetric crypto, we could be safe because the best thing we can do apparently for that is using a quantum algorithm that speeds up search in a set by square root of the size of the set. So if you double the key, you get rid of that problem. So if you are using AES, advanced encryption system, with a key that's double the size or some other method, you should be safe, apparently, according to the report by NIST. Okay, and what techniques do we use to develop postquantum cryptography? There are some of them that are maybe lattice-based, code-based, hash-based as well, and we're going to talk about the Isogeny-based cryptography. So in a second we will define elliptic curves, and one thing that you can do with elliptic curves is diffie-hellman, because they are groups, abelian groups. But the thing is, because of these quantum algorithms, this would be broken as well, but there's a way to recycle elliptic curves and reuse them for cryptography using isogenies. So next, how are we going to do postquantum cryptography? This is the longest part of the talk. If you get a bit lost, there's a demo at the end to visualize what we are doing, so you're going to be fine. How many of you know about elliptic curves? Okay, mostly. But let me review it. If you define this equation over some field, okay, A and B are in a field and satisfy this condition in order that they are smooth curves. And if you want to be more precise, you can take an extension of the base field and basically define this equation, and you say that that's the set of n rational points, and you add a point at infinity because if you homogenize the equation, there's only one point that you get at defining infinity, and it is the 0, 1, 0 point. Elliptic curves are groups. Why? If you have 2 points, here are P and Q, alright? You can take a straight line to them, then this line will always intersect the curve in a third point. By the way, this is the representation of an elliptic curve over the real numbers. And, well, you have 2 points, you take the third intersection of this line and then reflect around the axis, and this will be P plus Q, right? And you can prove that the set of k rational points of an elliptic curve with the operation that we defined is an abelian group. Right? So next thing we're going to say is how to classify elliptic curves. If you have this kind of equation, you can do this operation with the coefficients and you get a number which is called the J invariant. Take a close look at the 1728. It will be important in a couple of weeks. And well, thing is, 2 curves will be isomorphic over the algebraic closure of the field. You don't have to go to algebraic closure, it's a lower degree extension, but whatever. Even only if they have the same J invariant. And I will define what isomorphism means right now. And the thing is, for every element in the algebraic closure, you have a curve with J invariant that element. That means for every element in the field closure, you have an isomorphism class of elliptic curves, right? And notice that there are infinitely many of those. So next, isogenies. So you already understand why we're using isogenies. The The thing is, if you have two elliptic curves, we want to relate them by morphisms. But because elliptic curves are both algebraic curves and groups, we want the morphism to preserve both structures. So the first one is going to be a morphism of algebraic curves, and non-constant, by the way, so 0 is not something I will allow, and a group homomorphisms. Okay? And they have a standard form, which is this phi with p, q, s, and t polynomials. And well, it's useful to have this in mind because it's better to conceptualize. And I want to define a concept that is not in the slides, which is the degree, which is the maximum of the degrees of p and q. I don't care about the second component. Okay? And this has lots of properties, but I don't really need them right now. But just know that there is some degree notion. Okay, an example of isogeny is the multiplication by n map. For any group, you have this, any abelian group, I think, you have this multiplication by n map. In this case, this is an isogeny for every non-zero n. Because I said it's non-constant map. The kernel is written like so, and that is the group of n torsion points. By the way, if you didn't notice, we are defining isogenies for all the points over the whole algebraic loop. So this could be in some extension of the base. So, for instance, if we have the characteristic of the field that is positive and we have a prime that is different to that, we'll call L, and then for every n, the L to the n torsion has this structure. Okay? This is a group of rank 2 over Z mod L, and it has this quantity of cyclic subgroups of order L to the n. Right? This will be essentially the number of private keys that we can use when we define our system, our protocol. So next, I'm still with isogenies. It turns out that every isogeny has finite kernel, and it will be a finite subgroup of the curve, the domain curve. And there's this kind of, the implication goes the other way as well, because if you have an elliptic curve and a finite subgroup of the curve, then there will exist an isogeny having a kernel that group. And the isogeny and the image curve will be unique up to isomorphism. Right? So we call the image curve a quotient in a sense, okay? Because it's unique up to isomorphism, I can just say that. And this is easy to compute. It's not in the slides, but we have formulas that are basically the complexity to compute the isogeny is basically O of n, where n is the size of the kernel. Okay, let me change the point of view right now a little bit. Imagine from now that we are working with elliptic curves over finite fields. Then first thing we want to do is count the points, because there will be a finite set of points. And Hass's theorem just says if we are working over f cubed, use this power of p, then the number of points will be q plus 1 minus t, where t is bounded by the square root of 2 times the square root of q, which is a quite good bound, and basically means that the size is about q. Right? And now I will introduce supersingular curves. This theorem is usually not presented this way because you have to prove every implication, everything that goes into this. First one is the definition. Is supersingular if and only if the p torsion is trivial. Right? And this, actually the p torsion being trivial means that the morphism p is purely inseparable, but that's not important right now. What I want to look is at both conditions. The thing is that the t, which we call the trace sometimes, it's divisible by p. And also, if you look at the endomorphisms, tensored with q, there will be a quaternion algebra. First, what are endomorphisms? They are all the isogenies from the curve to itself, plus the zero morphism, with two operations, which are the sum and the composition of morphisms. This is the endomorphism ring. If you tensor it with q, you get which is dividing by every possible denominator, you get a quaternion algebra in this case. In other cases, you get a quadratic field. Okay? This quaternion algebra, by the way, is not commutative, right? And of course, the quadratic field is commutative. And why are they called supersingular? It's not because they have more. Well, they have double as many singular points as the original course because they had 0. But no, it's because they are really rare. Remember that for every element in the finite field closure, you had one supersingular J invariant. Sorry, one J invariant, not supersingular. But of supersingular J invariants, you only have P divided by 12, which is nothing compared to infinity. And that's why they're called supersingular, super rare. And right now we can already find SIDH. SIDH is supersingular, Isogeny, Diffie-hellman. You already know what all those words mean. And what's the setting? We will pick prime of this form, right? You could define it in more generality, but 2 and 3 are primes that work best for us. And we want this to be about the same size. And we will work over fp squared. Next, we will pick this curve, y squared equals x cubed plus x. I told you you have to pay attention to this number because this is the J invariant of that curve, right? If you compute the J invariant, basically because B is 0, the a's and the 4's will cancel and you will keep the 1728. And we pick this curve because it has, it's not the only one that has this property, but it has P plus 1 squared points over fp squared. This means that it has these many points, and therefore the 2 to the EA and 3 to the EB torsion will be defined over fp squared, right? Because they are rank 2 groups, we can take 2 generators, which we'll fix for the protocol, and then we can start picking private keys for this game. So what we'll do is Alice will choose a pair Mn modulo 2 to the EA and not both divisible by 2. And this will be her private key. Right? This is the, there are essentially 2 to the EA plus 2 to the A minus 1 pairs which you can choose. There are actually more pairs, but it turns out some of them are equivalent afterwards, and that's why I said the number of subgroups of this group. And then Bob does the same, chooses a pair Mn, but this time modulo 3 to the E, B, and not both divisible by 3. That will be his private key. And now we can do the exchange. What we'll do is taking the base of the 2 to the something torsion, we will multiply these numbers by, so do this linear combination and generate the cyclic subgroup generated by that point and do the quotient. Right? So Alice will compute the isogeny here, which is 5a, with this quotient. The isogeny and the quotient will be the secret key at the end. So that is the same. If you have the pair of numbers, you have this secret. But we'll do the same, and we'll call this, of course, AE and EA and EB. The thing is, we don't have, if they exchange just this information about what are these public curves, this is not enough, so that they can exchange keys. What you have to do is take the image of phi A of the elements of the base of the other pair. And Bob will do the same, phi B of PA and phi B of QA. With this information, they can multiply their integers by the base, or the image of the base of the other part, apply quotients to the public curve of the other part, and they will get the shared curve. But because everything is defined up to isomorphism, we can use the J invariant as a shared secret. Okay? So now let's see how an isogeny graph looks. Alright? Yeah. I'm sure it's that clear right now. Well, we'll do it. Do you see? Okay, do you want me to turn the lights off? Or? So this is the full isogeny graph for p equals 863. Right? The exponent for Alice is 5, the exponent for Bob is 3. That way 2 to the 5 is about 62 3, and so 32 and 37. And we start here at the yellow dot, right? This is E0, right? And Alice will do this red path using her secret key, and we'll end to EA. We'll end EA, and we'll send that to Bob, together with the auxiliary points. Well, Bob will start here as well, do this isogeny, this path here, and end in EB. By the way, the blue edges are 3 isogenies. 3 because of the degree is 3. Okay? And the red edges are 2 isogenies. So Alice travels through 2 isogenies, and Bob travels through 3 isogenies. And when they have these shared secrets, they can use their own private information. For instance, Alice gets this, EB, and then does using her information, this path here, and ends here, in the magenta dot. Bob does the same, and ends in the same shared secret. Alright? So this is how this works. I think this is maybe easier to understand the first time. and if you have, this is kind of Slavic here, but if you have a way of, in a general graph, making paths commute, you will be able to get and labeling the edges so that you have some kind of randomness, say. You will have a diffie-hellman in that sense, defined. Okay, so what are the complexity assumptions here? The first is the supersingular isogeny problem. This is equivalent to the discrete logarithm problem. You have the starting curve E0 and you have the public curve EA recover the isogeny. More precisely, recover the kernel of the isogeny. And as I said, it's analog to DLP. And the other problem is the supersingular Diffie-hellman problem, which is if you have all the information in the protocol, all the information you can see publicly, the points, the public curve, the starting point, get the shared secret. Of course, if you solve the previous one, you solve this one because you can act as Alice or Bob with the protocol, get the shared secret. And what's the security? Well, the same problems, at least the first one, in the ordinary case can be solved with a computer in super-exponential time. But for supersingular, we don't have this, I believe. I don't know if this is 100% true, but I believe this is because the algorithm uses the commutativity in the homomorphism ring, and we don't have this in the supersingular case. And then the best strategy to break SIDH is almost brute force, is the square root or fourth root of that. And this is exponential still in log p. And it looks like the auxiliary points could be revealing too much information. One of the creators of this protocol has said that he will not sleep comfortably with this problem until either someone breaks it or he retires. But looks like nobody has been able to break this. This is not 100% true because if one of the parts reuses their private key, then the key is actually breakable in a feasible time. But if you use random keys, what we call an ephemeral setting, then there's no problem. So next, there's some numbers. Okay, the first row here is numbers for some lattice-based crypto system. And the second one is SIKE. SIKE is the implementation of SIDH, the one that is submitted to the NIST competition for postquantum cryptography, and avoids the problem I just said, because it doesn't really only do diffie-hellman, it does more things, it does key encapsulation. You can see that the public key size is four times smaller than for the lattice-based system, but the earlier operations we are losing, because lattice-based systems are really fast, and this is an order of magnitude if you want slower. There are current efforts, but there is a metaphor I like very much, which is the ostrich and the turkey, because the ostrich would be the first system we saw, right? A very fast one, but with very large keys, while the other is the turkey, which is really slow, but small keys. And recently, this summer, there have been some experiments by some companies in trying to implement this in browsers and getting people to try them and see what works best. and obviously it looks like this one is winning, unless you have poor connection to the internet and then the other one is better. But there's still some work to do to improve the operations in the SIKE. Then, so some conclusions. We saw that publicly crypto systems would be broken in some years, Diffie, Hellman, and the like. There are current efforts in finding, but not only finding, but testing new postquantum standards, proposals, and right now SIDH SIKE is the most prominent extension-based cryptography protocol. But there are other constructions that we can explore. For example, there's the CGL function, the Charles-Gordon-Lauter, which is a hash function, and was one of the first protocols proposed. Then there is CSIDH, commutative SIDH, which works with the action of the class group over curves over finite fields. Then we can explore higher genus construction. As you know, elliptic curves are half genus 1. We can explore curves with higher genus and their Jacobians, moreover. And these are some of the references. I will post the slides in the SIMBa website, I think. And, well, I think this is everything. Thank you. Do you have any questions? Okay.
So in this graph, so in this graph, you're doing two iterations between the communication between Bob and Alice. So first Alice does the red path, then
Yes.
Bob does the blue path, but on the other side Bob does the blue path, then Alice does the red path.
Yes. Bob always does the blue and Alice the red.
Yeah, but
Yes.
I mean, like they share like half the path, so the same.
Yeah, I think you're right, yes. I'm not really understanding it, but
No. I mean, so their goal is to like join in the magenta dot, right?
yes.
I think there is. So in this picture there are two magenta dots.
Well, I think this is red and then this is magenta.
Okay, yeah. So the thing is that until the magenta dot, so Alice does a part of the path and then Bob does another
Yes.
part, and then the other way around.
Yes.
So first of all, why two? And then.
Okay. No, this is the same as in Diffie Hellman. So this is the same as you had this alpha to the A, okay, and Bob then raises this to the B. So what we're seeing, this is the operations. So you have the operations in Alice's machine and in Bob's machine. So we are seeing both at the same time. What is true is that this is not really interactive because you have to send the images of the points to the other part, right? So usually, what you could do is you compute your public key, you publish it in some place, somebody picks that and does an exchange, and that's the shared secret between you. In this case, you have to publish your the images of the points. This is the non-interactive part, and you have to decide which role you are playing, Alice or Bob, because there are different brands that you're 2 or 3 that you are using. But no, yeah, what you're saying is
Actually, the communication, so to say,
yeah, the communication
red
happens
dot.
here, between here and here, right? And this happens at the same time.
Okay.
There was some other question?
Well, this is a question of someone that doesn't know algebra.
That's good.
So my question is, what makes elliptic curves so special? Or if you know if there has been tried to generalize this concept to another kind of polynomials, for
Yes.
example?
Yeah, yes. For example, when I talk about, I will restrict very much because they have so many applications and connections with a lot of things. But if we restrict to the cryptographic setting, for instance, I talked about higher genus. This is taking for instance, you could use hyperelliptic curves. This is taking the same equation, and you take y squared equals something, but instead of something that is degree 3, you take something that is higher degree, so to speak. And you have some problems with that because then you have that is not really the curve that you will be using, but that's the basis. Then you will be using those those points and generating some huge vector space, well, huge models to work with that. But, and that's one of the things. Of course, there are lots and lots of connections and generalizations. That's one. And I don't know. Yeah.
Yeah, I think it was Google that said that they built a quantum computer
Yeah.
that solved an algorithm in 1 minute and 20 seconds.
Yeah, I haven't really read the paper. I should, but they called it quantum supremacy. Something came out 1 or 2 months ago. People. So I have seen some reviews of it in the internet, which are saying, okay, we are not really there for some things. So for solving discrete logarithms, I don't think we're really there. The current, for integer factorization, for example, the current record was a couple of years ago, factoring 21 into 3 times 7, which is, okay, it proves that the algorithm works for small numbers, but there's still more development needed. This was a couple of years ago. If they are putting so much money in it, of course, they will have some advancements, but I don't think we're there yet. As far as I know, because I don't know everything that's happening right now. Yes.
Yeah. When you define diffie-hellman, you need just like 2 groups, and you are using the property that these groups are not commutative, but you are using an elliptic group. Am I right?
So with the 2 groups, you say the 2 elliptic curves?
Yeah, but you two isogenies, there are quotients
Yes.
by 2 different subgroups of the group.
Yes.
Of the elliptic. And these subgroups are not commutative, or are they?
They are, because they are cyclic.
So if
Each
you
one of them
do
is cyclic.
the same construction with like any general group with 2 subgroups, or do you need something critical about elliptic curves to do this
No,
construction?
I was thinking about this the other day. I think you could do it maybe. So picking a group, picking a cyclic subgroup, or not cyclic, just some subgroup, you can do the quotient. As long as doing the quotient is easy, and then recovering what the morphism is between the two public is hard, that would be a way to generalize this. There's a thing, because isogenies are surjective morphisms, so they have some more properties than I have explained. Also, the degrees, for instance, which are kind of important for us for ensuring this works, is multiplicative. You have, maybe you don't need the notion of degree to define this, I don't know. But if you need it, if you find some point in which you need it, well, you will have to develop that notion as well. Yeah, but it could be and I don't know if you need the groups, the general groups, to be abelian. So the elliptic curve is abelian. The question is easy to make. Maybe if it's not commutative, who knows? Look for normal subgroups, you're restricting. I don't know. Some other question? So let me say a couple of things. First, Nelly said that we wanted to do some seminar at some point of time, working with homology, I think it was. So if anyone is interested, now come talk with us and we'll try to arrange that. And then, so Andrea mentioned